Test 4 review. I will be expecting that you have read the problem and are ready to start answering the questions. Okay? So, looking at problem number 1, I'll pause, allow you time to either pause the video or read the problem. Find the best point estimate for the population mean. Anytime you want to estimate a population parameter, simply replace it with the word sample. Okay, so if you look in here, the sample mean was 7.2. So that's A. B, find a 95% confidence interval for the mean number of jobs that a retired person has held over his lifetime. So we're looking for a confidence interval associated with the mean. So we know that's between one of two formulas. We look up here, we know what the population standard deviation is. In other words, we know what sigma is. So we will be working with x bar plus or minus z sigma of x bar. Okay, now I'm going to assume you can work with the t-table. So I'm going to just be pulling numbers out. We know that x bar is 7.2. The z-score associated with a 95% confidence interval is 1.96. And then sigma of x bar is sigma from the problem divided by the square root of the sample size, which was 40. When you calculate this, you should get approximately 0.32. Now, when you plug this into the formula, you're going to get 7.2 plus or minus 1.96 times 0.32. You can do the math from here, but the actual interval will be given by, well, I'll put the plus or minus here for you, 0.63. Okay, so the actual interval is 657 to 783. Problem number 2. C. Find a 99% confidence interval for the mean. Okay, so here the only difference is, instead of working with z of 1.96, the only difference is z is 2.576. So you substitute it into the formula. 7.2 plus or minus 2.576 times same standard deviation 0.32. Do your math and you're going to get 0.82. So if you add and subtract, your actual interval will look like 6.38 to 8.02. Okay, so that's the first problem. Moving on to the next problem. Here's problem number 2. Again, pause the video, read the problem. I'm going to start working the problem. In this particular problem, we are looking for a 90% confidence interval for the mean. So again, it's between one of two formulas depending upon if we know the population standard deviation or the sample. Well, when you read this problem, we are talking about a sample. And we continue on, so we have to assume that the sample deviation here is associated with the sample. And so we will be looking up a t-score, because working with the sample standard deviation, our formula looks similar, but the main difference is we're looking up a t-score. So there's our formula, chapter 7. We look in the problem. X bar is 33.2. We now look up a t-score. In order to look up the t-score, we need two pieces of information. The confidence level, 90%, and then the row number, which is the degrees of freedom, which is the sample size, 15, minus 1, which is 14. So when you look up 90% confidence interval, row 14, you should find a number t equal to 1.761. We're ready to plug everything into the formula. 33.2 plus or minus the t-score, 1.761, times the, oh, we forgot the standard deviation, right? Okay, well, the standard deviation is the standard deviation from the problem divided by the square root of the sample size. Doing your math, you should get 2.58. All right, so now we have 2.58. We do our math. One time we'll add, one time we'll subtract, and that would be the actual 90% confidence interval. 28.66, 37.74. So that's problem number 2. Problem number 3, take a minute to read the problem. Okay, so if you are ready, this is an hypothesis test. Why? Someone is making a claim. They're claiming that state employees' average salary is less than that of a federal employee. So our first step is to come up with the null hypothesis, which is what is the claim being measured against? The benchmark. The claim is being measured against the salary of a federal employee, which is this number up here. Federal employees make on average $59,500. The alternative is the claim. The claim is mu is going to be less than $59,500. Once again, these two numbers are always the same, and it's not associated with the sample. Our second step is to come up with the critical region. The critical region is based, one, upon the alternative hypothesis. We want to be less than wherever the assumed correct mean is. So we want to be down here somewhere. Oh, just erased something by accident. All right. Well, anyway, let me write it down here right quick. H naught. Mu naught is 59,500. H1, mu is less than 59,500. Critical region. Again, we want to be down here somewhere, below some number, because the mean is located here. Now, that critical region is also based upon a t or a z-score. So is it t or z, right? Well, once again, we go looking for the population standard deviation. There it is. So we know it's going to be a z-score. The z-score is associated with the level alpha, which is 0.10. We only have one tail, so we're going to work with alpha of 0.10. We look that up on the t-table at the very bottom of the z-scores, and you find z is equal to 1.282. So since we're to the left side of mu, we're going to insert negative 1.282. 2. I think I might make my mark a little bit skinnier. Okay. All right. Next step is the test value. The test value is one of the get to the table formulas. For us right here, it's x bar minus mu naught divided by sigma of x bar. X bar is in the problem, mu naught's in the problem, sigma of x bar we need to calculate. It is 1500 divided by the square root of 20, sample size. And so we end up with 335.41. Now we're ready to calculate the test value. X bar in the problem is 58,800. Subtract the mean, which is 59,500, divided by the standard deviation, and our test value turns out to be negative 2.09. Now, this negative value is located somewhere down here, which is in the region of rejection. So our conclusion is we reject the null hypothesis. And then we have the possibility or possibly a type, well, which error is associated with rejection? Type 1. So there's problem number 3. But then we find out that there's a part B to problem number 3. And part B is the same test, but using a different level of significance. So the only thing that changes here is the critical point, the point that separates the rejection region from the non-rejection region. In other words, we're still working with the z-score. Our level of significance 0.01, but now our cutoff point for the rejection region is going to be this score, z equal to negative 2.326. Now using this level of significance, see, we're putting more demand on the person making the claim that they're correct, because when you decrease the level of significance, you are spreading out the endpoints where you're going to reject. So it makes it harder for the sample mean to be out that far. So in this case, we're not going to reject because our test value is still the same, and our test value will be somewhere up in this region. So our conclusion is we do not reject. H naught, so it's possible type 2 error, non-rejection when we should have rejected. There's problem number 3. Okay, again, read the problem, pause the video, and we get started here. Once again, we have an hypothesis test. Now on the final exam, you're not going to see any of this stuff down here. Down here, you're not actually going to see that. Okay, but we have an hypothesis test, and this test is asking us to determine if a franchise cost is different from the national average. Okay, In other words, a nationwide franchise thinks that its cost is different from this average. So, the null hypothesis is based upon what the claim is and what is it comparing itself to. It's comparing itself to the mean of 5,400. The actual claim itself, which is the alternative hypothesis, is that this is different. So, there is the hypotheses. The critical region is going to be a two-tail region, because here's the mean, but it's saying it's different. Different means less than or greater than. Now, is this a z-score or a t-score? Looking back up at the problem, we took a random sample that had a standard deviation of 629. So it's going to be a t-score. Now, in order to determine a t-value, we need one, alpha, which is 0.10. But when we look over here at the critical region itself, we notice that we have two tails, so we'll be dividing alpha in half. So we'll actually be looking up 0.05. In order to look up a t-score, we need to know the row number, which is the degrees of freedom. The sample size was 28. Subtract 1. We're working with row number 27. From the table, we get t is equal to 1.703. Now, 1.703 goes here, but since this is the left side, we put in a negative 1.703. Our test value will be based upon x bar, which is 5250. Mu naught, which is 5,400. And our standard deviation, which is the standard deviation divided by the square root of the sample size of 28. That number comes out to be 118.9. So now our test value is 5250 minus 5,400 divided by 118.9. Do your math, and you'll get negative 1.262. To draw a conclusion, we identify where this is located on our graph. A negative 1.262 is somewhere down here. It's above this number. It is in the non-rejection region. We do not reject. H naught. So we did a possible type 2 error. Type 1, rejection. Type 2, non-rejection. There's number 4. Problem number 5. Read it over and we'll get started. In this problem, we are trying to find a confidence interval for a proportion. Confidence interval for a proportion. We know what formula we're going to be working with. P hat plus or minus z of sigma. See, I don't have a simple eraser here. Well, It's going to be p hat plus or minus z sigma of p hat. P hat is the sample proportion. 65 out of 250 believe in haunted places. 205. Changing that to a decimal number. Z is associated with the 99% confidence interval. Look it up in the table. 2.576. Sigma of p hat is the square root of p times 1 minus p divided by n. But we don't know what the true proportion is. So since we don't know what it is, we're going to substitute in 0.32. And we get the square root of 0.32. 1 minus that is 0.68. Divide that by n, which is 205. Do your math, 0.033. So, using our formula, 0.32 plus or minus z, 2.576 times 0.033, 0.32 plus or minus the product of that, which is 0.085. So I'm going to round this to 2 places itself. And here's the actual interval form. Adding 0.09, subtracting 0.09, we have, that's supposed to be a dot, we have a 99% confidence interval where the true proportion will be between those two numbers. On to number 6. Read the problem. As you can see, this is a hypothesis testing about a proportion. So once again, we start off with the hypothesis, the null hypothesis. This store manager is claiming that the proportion of his customers who prefer self-checkout is larger than 43%. So he's comparing against the benchmark. So the benchmark is the null hypothesis. His claim is that P is actually greater than the null hypothesis. We come up with the critical region based upon the alternative hypothesis. The claim is that it's larger. So we're in this direction. So we have to look up a T or Z. For proportions, it's always a Z. Alpha is 0.01. We have one region, so we leave alpha alone. We look up the Z-score, 2.326. So that's our number here. That is the critical point, the cutoff point between the non and rejection region. Move on to the test value. Again, P hat is the sample proportion. He took a sample of 36 people. 19 out of 36 preferred self-checkout. That comes out to be 0.53. P naught is from the null hypothesis, 0.43. And sigma of P hat, again, is the square root of P times 1 minus P divided by N. But we're assuming P naught is correct, so we're going to be working with the square root of 0.43 times 0.57 divided by n, which is 36. And if we do our math, we get 0.083. So our test value is going to be 0.53 minus 0.43 divided by 0.083. Doing the math, 1.20. Now you should be practicing the math. Even though I'm going through this fast, I have my numbers written down already. But you should be practicing your calculator. So there's our test value. Once again, that test value is located somewhere down here, not in the rejection region. So we don't reject H0. So since we did not reject, we could have committed a type 2 error. Okay? And that's it. So good luck on the test.